we're going to try and get through this 8.7, and then hopefully we'll be wrapped up with chapter 8, and you'll be done with sequences and series, which is good. So I know it was a while ago, but we discussed the Taylor and Maclaurin series, which gave us a formula for generating a power series for a given function. And the last example I did in class was we did the Maclaurin series for cosine x. All right, and that's what we came up with. So if you look back in your notes, that's what we did. I'll show you because, again, it was Thanksgiving. I know you may have forgotten what we did. We started out with cosine x. Here was our formula that we used. It meant that we had to take a bunch of derivatives of the cosine function and then evaluate it at a here being 0 because it was a Maclaurin series. And then once we did that, these values here represented the coefficients of our power series. Then we always divide by n factorial. It's always x to the n. Then we wrote it out. And what we determined was that every term that we have for cosine is an even power of x. And so I was telling you how that's why we call cosine an even function. Do you remember that a little bit? And, you know, what did it mean to be even? And this is what we came up with right there. So that's where I want to pick up today, because what we didn't do is determine a radius of convergence. So the question would be, you know, can I trust this formula for all x's? So would this formula work for cosine of 3? Would it work for cosine of 10 pi? You know, any value? Or is there a certain range of values I have to keep my x in for this formula to hold? Right? I mean, we talked about convergence and divergence of power series. Here's one right here. Let's see its radius of convergence. So what I would do is apply the ratio test. So we are now going to find the interval of convergence for cosine x. So we'll set up a ratio test, right? The ratio test will be a sub n plus 1, the absolute value of a sub n plus 1 over a sub n, which we already know you do the reciprocal thing. So we'll have, do I need the negative 1 to the n? Do I really need that? It's going to go away, so it won't matter. I'll have x. Now here's, again, a good practice on this. X to the what? 2 what? 2n plus 1, but if we distribute that 2 through, it'll be 2n plus 2. Again, those are the little things I saw in the test. And then on the bottom, 2n factorial is 2n plus 2 factorial. Again, same thing, that 2 distributes through. So we have 2n plus 2 factorial, right? So that's a sub n plus 1. Are there any questions on that? Because I did see quite a bit of mistakes on that on the test. Everyone's comfortable with the 2n plus 2? 2n plus 2 now? Okay, I multiply that by the reciprocal of a sub n, so this will be 2n factorial on top and x to the 2n on the bottom. And then now what I try and do is start getting things to cancel. Oh, wait, hold on. I want that to be what? For this to converge, I need this to be less than 1, right? Pardon me? Yeah, oh yeah, forgot my limit out here. Limit n goes to infinity. Need that. And let me just rewrite some stuff here. This is limit n goes to infinity. I can rewrite x to the 2n plus 2 as x to the 2n times x to the second power over. Now the 2n plus 2 factorial, I wrote it down up here because, again, there were some issues on the test with that. You're peeling off one at a time, right? So you're subtracting one from this, subtracting one from this. That's how you peel each factor off. So it becomes 2n plus 2. Why am I doing this? Why am I peeling off? 2n plus 1. So I can get the 2n factorial to cancel with the 1 on top over there. So I'm going to stop there at 2n factorial. And then on the bottom, x to the 2n. I need that to be less than 1. And I get some good cancellation here. The only thing that's left, limit n goes to infinity. Let's see. I'll split it up into two things. It's 1 over 2n plus 2 times 2n plus 1 times x squared. Need that to be less than 1. So what happens here? This is, yeah, you can take it out, right? Where does that go though? 0, right? That goes to 0. And so does it matter what x is? No, it doesn't, because this is going to go to 0. It's going to kill off my x term right here, my x factor. So this is looking like 0, which will be less than 1 always, right? For all x. Right? It will be true. So that means my interval of convergence is what? All real numbers, everything. So my interval of convergence is negative infinity to infinity. That's my interval of, I'll call it IC, interval of convergence. So it always converges. And that's good to know. It means I can trust that formula is good for all values of x. Okay, so the next one I want to do, we did cosine. I'd like to do sine. I'll move a little quicker than I did last time, though. Let's find the Maclaurin series. Series for f of x equals sine x. So according to Taylor's theorem, right? Taylor's formula, we have that f of x can be rewritten as a series, sum n equals 0 to infinity, of the nth derivative of f evaluated where? In this case, at 0, right? Because it's a Maclaurin series. But the Taylor formula says that this should be a, right? For us in this problem, a is 0 because that's what Maclaurin series means. A is 0, all right? So I'm going to replace it with 0. And then it would be over n factorial. That's always the case. And then x, normally it's x minus a here. Okay, it would normally be x minus a to the n, but because a is 0, I just write x to the n. Right? So that's our Maclaurin series. That's our formula for it. So I'm going to need some derivatives, and I'm going to try and get a pattern if I can. So let's list out some derivatives here. What is the 0th derivative of the function? Cosine x, right? Oh, sorry. It's sine x. The 0th derivative means I'm not taking a derivative. Now, what's the first derivative? Cosine x. Second derivative, negative sine x. Third derivative, negative cosine x. Fourth derivative, sine x. So we're back where we started, aren't we? And that's just going to repeat that pattern, right? The pattern that's being repeated is this block of 4 things, right? Sine x, cosine x, negative cosine x, then sine x, cosine x, negative sine x, cosine x, and it keeps doing that, right? So now, in our formula, we don't want to know the nth derivative at x, right? We want to know the nth derivative at 0. So what I need to do is come in here and just plug 0 into all of these now. So on the side here, I'm going to say, well, the 0th derivative of f at 0 would be sine of 0, 0. The first derivative of f at 0 is cosine of 0, which is 1. The second derivative of f evaluated at 0 will be 0. And then the third derivative of f evaluated at 0 will give me -1. And then the pattern will repeat, right? So from here on, it'll be 0, then 1, then 0, then -1, and it'll keep going. So what we should do now is go back to this formula, right, and just start plugging in n equals 0, then 1, then 2, and start writing things out. Because we know what the first, 1, 2, 3, 4 are. Actually, we know the rest of them too, right? And what we'll do is when we write them out, hopefully from that writing it out, we'll see a pattern and we'll be able to rewrite this formula where we get a power series, like something we can do a ratio test on and things like that. So let's write out the terms of this series. Okay, so f of x equals sum and equals 0 to infinity and through. I'm just rewriting what I had up there. This should be equal for us in this particular problem to be first n is 0. So when n is 0, what was our derivative up here at 0? It was 0, right? So we're going to get 0 over n factorial will be 0 factorial, right? I mean, I'm already done, but I'm just writing it out, okay? And then x to the n, which is 0, right? So that's my first term. Now I move to the second term with n being 1. All right, so what was the first derivative evaluated at 0? It was 1. So I get 1 over, and now the bottom is 1 factorial, and then x to the first power. Then we'll have, okay, what's the second derivative, right? We're at n equals 2 now. 0 over 2 factorial x to the second power. Then the next one will be -1 over 3 factorial, and then x to the third. And then what would the next one be? 0, right, over 4 factorial x to the 4. I'm going to try and get one more in here. Plus, we're back at 1, right? 1 over 5 factorial x to the 5th. And it keeps going, dot, dot, dot. I'm hoping that that's enough for me to pick up the pattern. A lot of these things go away, right? 0 here, 0 here, 0 here. All the even powers of x are gone, right? And so what I'm left with is an alternating series, right? It's an alternating series. It starts out positive, doesn't it? And then it becomes negative and then positive. So I'm trying to write out this series right now. How do I create alternating? Well, -1 to the, and I want it to be to the positive first, right? So n plus 1 would work. So that creates my alternating series, starting with positive terms. And then what's happening, see, the tops are always 1s, right? It's just alternating. So I don't have to worry about that. The denominator are what? Factorials of odd numbers, right? Odd factorials. So how do I create odd numbers? 2n plus 1 or minus 1, right? So it all depends on what our n is going to start at. Starts at 0, so I want to start with 2n plus 1, okay? So I'm going to put that on the bottom. I'll just write it like this, and then I'll throw it all together. I'm out of room on this page, so that's why I'm doing it right there. Okay, we all agree that this is going to create odd numbers starting with 1, and then throw the factorial on it. And then the rest of it, my x, right? These are all powers of x, but they're all odd powers. So how do I create odd powers? 2m plus or minus 1 in this case again, because What do I want my first power to start at? 1. So I do it 2n plus 1 again up here. That good? Now, I'd like to go back and just, if everyone's got that down, I just want to look at the cosine again. Very similar, right? I mean, very similar. Wait, hold on. Was that plus 1? Hold on. No, hold on. When I wrote it down over here, n equals 0, did we not write down here? It should be, go back here. We may have just brain farted here. Look, this right here needs to be fixed. That's what it is. N is starting at 0, right? So if I plug in 0, what's my first term going to be? Negative. I wanted it to be what? Positive, right? I guess we're all a little slow today, right? This should be just what? N, right? Because then I plug in 0, negative 1 to the 0 is 1. And then when you go to 1, okay, so I was trying to point out how similar they were, but then those were off. So that kind of alerted me. Everyone okay with that? That's n, not n plus 1? Everything else is okay. Now, compare that now to the cosine, and what's the only difference? Just right here, this 2n right here, we have 2n plus 1 on the other one. On this one, we have 2n. So this gives you the even powers. The other one gives you the odd powers. So I had talked last time about cosine being an even function because the powers are even. Sine is an odd function, obviously, because the powers are odd. All right. Any questions on this? How about interval of convergence? You could do that. Ratio test, and then I'm not going to go through it, but I'll just tell you that the interval of convergence for this one is also negative infinity to infinity. All right? I think now would be a good time to point you to a page in the book, and I don't have the book with me, but I believe I did write it down in here. Someone open up to page 484. If you have it, do you see on 484 a list of common do y'all see a list of common power series or Maclaurin series? Okay, I'm going to try and bring it up real fast. Got this weird thing going on with my laptop. Only when I'm on Mozilla Firefox. Pages won't load unless I'm moving my mouse around. It's apparently a known issue, but only certain laptops, it's only happening on, I think, laptops and only certain laptops, and it's really a pain in the ass. So I have to sit here and do this. And I would just use a different web browser, except for I've got all my bookmarks up here, and I don't want to have to redo everything. Okay, what page is that? 8.7. Oh. There. 484, yeah. So this is very common, all right, that, in a different class, you won't be asked to go find the power series. You'll actually just have a table of power series, and you'll, refer to it. So what we have is, here's our sine x, right? We just did this one. Is this power series, which is exactly what we had, right? And now you see where this comes from, though, right? It comes from the Taylor or Maclaurin formula. And then cosine we did last class also, all right? Now, e to the x, I have that on my list of things to do. Shall we, or do you want to do e to the x? Figure it out? I'm going to show you that, but I need to show you e to the x first before I can show you that. Yeah. Let's do the e to the x, all right? It'll go pretty quick. Okay, so now let's do Maclaurin for f of x equals e to the x. All right, I already know I'm going to need a bunch of derivatives, right? Right? But the nth derivative of x is itself, no matter what, for all n, right? Upside down a means for all n. The nth derivative of f is e to the x. So because this is Maclaurin, I want to know what you get if you plug 0 into those. So what's the nth derivative evaluated at 0? E to the 0, which is 1. So all of your coefficients are 1. Do y'all see that? No matter what, you'll always get, when you plug 0 into e to the x, you always get 1. So when I start to write out the terms of this thing, I'm going to have 1 for every one of them, right? It's not going to alternate. I don't have negatives here. It's just going to be 1, 1, 1, 1, 1 on top, right? On the bottom, we're going to have n factorial. So it's going to be, you know, like 1 factorial, next one will be 2 factorial, then 3 factorial, then 4 factorial, so on and so forth. And the powers on x just keep coming up. Does that make sense? I mean, basically, it turns out to be this. Sum n equals 0 to infinity. That nth derivative up there, we said would always be 1 over, right? The bottom will be n factorial. And then this will be x to the n. So I guess all I'm trying to show you is that since that's always 1, this part never changes, then the formula is just these two pieces, which is the same for all Taylor series, all Maclaurin series. Well, all Maclaurin series would look exactly like this. It's just this thing in front that dictates the rest, you know, what's happening. So if we just start writing some terms out here, if n is 0, what do you get? Well, 0 factorial we said was 1, right? So you get 1 over 1, then x to the 0 is 1. So you get 1 plus x, right? That'll be the next one. See, right, n is 1, you get 1 over 1, x squared. Then you get, what, 1 over 2x squared. Then you get 1 over 3 factorial. I should have put 2 factorial here, but same thing. X cubed plus, and you keep going. And I already showed you when we first started talking about power series that if you actually take the derivative of this power series, don't you get the same power series? The same exact one? Yeah. So, you know, it's a really nice property, I guess, of e to the x, is that it's the only function that does that. So that matches exactly, it should match exactly what we have here in the book. They just took the 1 out of there. They just put x to the n over n factorial. Okay? Got it? Okay. So let's take a look at doing a Taylor series instead of a Maclaurin series. All right? Just what's the difference? Yeah, it's not, A is not 0. So let's do a Taylor series. For f of x equals, let's do e to the x again, about 2. In other words, we're not going to do the Taylor series about 0. We're going to do the Taylor series about 2, meaning a is 2. So this tells us right here, a is 2. So let's just take a look at how the formula changes. All right? Taylor, the formula tells us that this will be sum n equals 0 to infinity, so that doesn't change. We still have the nth derivative, right? But instead of at 0, it's where? At 2, right? And then we have down here still n factorial. That never changes. But instead of x to the n, we have x minus 2 to the n. So what you have to go figure out now is what's the nth derivative of f evaluated at 2 instead of 0? Well, don't we already know the derivative of f is always going to be itself, right? E to the x, e to the x, e to the x. And if I say now plug in 2 instead of 0, what are you going to get? E squared, e squared, e squared, e squared for all of them, aren't you? So this part right here is always going to turn into e squared. Now, be careful. The only one that's going to behave like this is e, right? All these other ones like sine and cosine, that would change, right? It would be different. And we'll do one of those, all right? I'll do one where we'll do like, well, let me see. I had one ready to go here. Where is it? Nah, that one's boring. There we go. I've got one coming, all right? After this. Okay, so let's write this out. What do we have? We've got, just write out a few of the terms here. We've got e squared over 0 factorial x minus 2 to the 0. Then plus e squared over 1 factorial x minus 2 to the first. Plus e squared over 2 factorial x minus 2 squared, and that continues on. Now we're not going to be able to put this into a cleaner looking thing. I mean, this is the actual series right here. All right. I mean, we could rewrite. The best we could probably do is this: sum n equals 0 to infinity of e squared over n factorial x minus 2 to the n. In other words, actually go in and replace that derivative part with e squared, and then that's about as good, as condensed as you're going to be able to get the formula. Because imagine each one of these, like out here, these start getting like squared. You have to expand that out, and then cubed would be the next one. That gets pretty nasty. Do y'all remember what we were actually doing when we were changing the a? Do y'all remember in the picture that I did a long time ago? We were shifting it. I had shown you that for some of these series, it did real good within a certain window, and then outside that window, it didn't do good at all. But I said it's okay because we can always shift it. So this would be a shifting. Now, you would never shift e to the x. And the reason why you'd never need to shift e to the x is because guess what its interval of convergence is? Everything, okay? You'd only want to do like a shift if your interval of convergence was actually something other than everything, and you would just shift it over to where you were interested in. So I didn't mention that on this page, but notice on the end of this, next to these, do you see where it has this? Okay, this is your radius of convergence, which basically is it's telling you the length of your interval of convergence. So this is saying, look, e to the x, that works for all x's. Your radius convergence is everything. Sine x, same thing. Cosine x, okay, now arctangent, different. That is going to have radius convergence of 1, which means its interval convergence has a width of 1, or a radius of 1, so 2, and you'd have to move it back and forth wherever you'd want it. Same thing with these, all right? So just be aware that there are tables like this that are utilized in, classes like differential equations, and where you're, okay, well, let's just look at the power series, and you just go to a table. They don't really expect you to generate it by hand. Okay, any questions about that? All right, let's take a look at another one. Let's do the Taylor series for f of x is natural log x about about 3. So here's what the formula tells us. We're supposed to go try and figure out what this series is doing. It's n equals 0 to infinity. The nth derivative of f evaluated where? 3 over n factorial times x minus 3 to the n. All right, I've got to go investigate that. So I need to go take some derivatives. Now, unfortunately, natural log of x does not behave like e to the x, does it? So that's life, right? That's the way it goes. So let me start looking at derivatives, all right? Start out with the 0th derivative of f. What is that? And notice I'm not going to plug in 3 yet. I'm just going to say, what is the derivative? Treat it like a function. That's just itself, right? Okay. Now, what is the first derivative of natural log of x? 1 over x. 1 over x. Which, because we're about to take derivative again, I just remind you this is x to the negative 1, right? Okay, so the second derivative will be what? Negative 1 over x squared. That, I'm just doing power rule, right? Negative 1 comes out, subtract 1. Okay, what's the third derivative? Positive now, right? Because you'll have 2 negatives there, so. And then the next one will be negative 1 over x to the 4th. Yeah? And this just keeps happening, right? What's happening is it's alternating sign, right? And every single time it's getting 1 power larger. I'll do one more. This would be what? Positive 1 over x to the 5th. Okay, so can you please give me a formula for the nth derivative? Negative, okay, so you're trying to take care of the alternating part, right? The negative 1 to the what, though? Yeah, the 0th one I don't really care about, okay? Starting here, right, I want the first derivative to give me a negative 1. The second derivative, positive term, right? I want the first derivative to give me a positive term, the second derivative to give me a negative term, the third derivative to be positive. So for odds, I need positive. For evens, I need negatives, don't I? So how do I make that happen? N plus 1. So does everyone agree that if I plug an odd in, I'm going to get a positive, and if I plug in an even, I'm going to get a negative? Yes? Now, what's happening on the bottom? It's x to what? The n power, right? X to the n power. There's something missing here. Well, there was something missing in these derivatives, and I think we need to go a little slower through this. All right, let me do it this way. Come back up here. Do you see what we're not dropping down numbers? Okay, look. When you took the derivative of this, what happened? Negative 1 came out, x to the negative 2. Let me write that down right here. That was negative 1 x to the negative 2, right? Which turned out to be negative 1 over x squared. But what would happen if I take the derivative of this now? What would I get? Positive 2 x to the negative 3, right? No one seemed to mention that those powers are going to factor in, aren't they? Right? What would the next one be? Negative 6. Now, how am I getting the negative 6? 2 times. Okay, so what I'm getting at is you need to cross these out. Negative 6? Can I write this another way, please? Negative 2 times 3, x to negative 3. Is that okay? Negative 4. Why am I writing it that way? Are you seeing the factorial coming to life here? What would the next one be? Positive 2 times 3 times 4, x to the negative 5. What would the next one be? I'm not going to write down, but what would the next one be? Negative 2 times 3 times 4 times 5, x to the negative 6. So we need to rethink this formula here. Well, the negative part I think we're good with, aren't we? I mean, getting the back and forth negative. It should still be negative 1 to the n plus 1, right? But what's next to it over here? It's n minus 1 factorial. Right? It's not quite n factorial, right? If we want the fifth derivative, right, this was negative 5 up here, and this was 1 less than it down here for the factorial. This was 4 up here, this was our 4, and then this was our negative 4, and then this was our n minus 1, 4 minus 1, 3 factorial. Did I lose everyone on that? I mean, is that something I have to start completely over and just like clean the slate? Are y'all okay with that? Right. This is our formula, right? This is a good formula for this part, right? Except I have to do what? Plug in 3 into all of those. So what would happen if I plug in 3 for what? For x? Wouldn't that just replace that with the 3 right there? Isn't that all that would do? So what I'm getting at is that I could go in here and start plugging in 3 into all of these. But at the end of the day, it's equivalent to plugging in 3 into that, which would be negative 1 to the n plus 1 times n minus 1 factorial over 3 to the n. Now, are you okay with this formula always working for n? I mean, did our formula always work for n? Except for that very first one, right? That very first one. It didn't work, did it? Like if you try and plug 0 into this for n, that's not going to give you the natural log. So we're going to pull it out, yes. So just keep in mind up here that the 0th derivative at 3 would be what? Natural log 3. Okay, so can someone help me write out the formula for the natural log of x about 3? Okay, so the natural log of x, sorry, f of x should be that first term, which was just natural log 3 over 0 factorial x minus 3 to the 0, right? That's our first term. That's when n is 0, right? When n is 0, it doesn't follow the pattern of my formula. But the rest of it does. So what I'm going to do is say plus summation n equals 1 to infinity. Because remember, I already took care of the 0. It's right there. That's the 0. I peeled off the 0 because it doesn't follow the pattern of the rest of the thing. Now this is going to be what? That negative 1 to the n plus 1 times n minus 1 factorial over 3 to the n over n factorial times x minus 3 to the n. Did I lose y'all? Remember this part right here, that right there is our f n at 3, isn't it? This right here, in Taylor's formula, this is that part. We found a formula for it. And now what we could do is we could try and clean this up. Could we do some cleaning up on that? where does this n factorial really belong? Like if I could put it right next to this one, right? And then I could use this n minus 1 factorial and that n factorial. I could peel one off of the n factorial. So I'm going to rewrite this. This is equal to, this first one becomes just natural log 3 times what? X minus 3 is 0 is 1 plus summation n equals 1 to infinity of negative 1 to the n plus 1 over n minus 1 factorial, or sorry, times n minus 1 factorial, times 3 over, gosh, man, I think I'm ready. I'm ready to call it a semester. How about you? Can't talk anymore. So all I did there was brought this one here and then rewrote it, right? Rewrote it as n times n minus 1 factorial. That's the same as n factorial, right? This is the same as n factorial. So I cancel out the n minus 1 factorials like that. That's about as clean as it's going to get. I don't think there's anything else I can do. That's right, it comes down. Yep, it comes down. So, yeah, remember, anytime you have a factorial, n factorial is equal to n times n minus 1 times n minus 2. So if I wanted to, I could have stopped right there and just put the factorial on the n minus 1, right? N minus 1 factorial would mean n minus 1 times n minus 2 times n minus 3. So this factorial is only on this piece right here. The n just got peeled out, which is that. So a final version of this would be natural log 3 plus sum n equals 1 to infinity of, let me see, I'll write it this way, negative 1 to the n plus 1 times x minus 3 to the n over n times 3 to the n. I wish I wouldn't have messed those derivatives up in the beginning, but I hope you followed that. So, you know, with the one with sine, we noticed that the pattern of the part here in yellow, right, which is in our formula, right, in this formula, the n factorial won't ever change. This will depend on if a is 0 or 2 or 3. This part right here, we either find a pattern for it, like sine, right, was alternating. It was like, you know, 1, 0, negative 1, 0, right? Or like with e to the x, it was always 1, or it was always e squared, which was nice. Or like with the natural log one, there wasn't a pattern, not really, so we actually came up with a formula for it. And we used that formula there. So those are like the different variations of what you could see. Is that good? Okay. All right. Now, I'll show you a couple of applications of this. All right. So here's an example. I would like for us to integrate from 0 to 1 sine x cubed dx. This is a good old Cal 2 problem. Remember when y'all took Cal 2? It's a definite integral, right? Which means that geometrically, this represents what? I mean, just like a very basic idea here, this integral represents what visually? That's right. It's the area under the curve sine of x cubed, graph sine of x cubed between 0 and 1, and look at the area below the curve, right? That's what it means. And I already took the liberty of doing that for you. So I'm interested in that area. Right now, that area could be interpreted different ways, right? It could represent, since it's an integral, definite integral, it could represent some sort of, you know, trying to think of some of the things. We talk about mass, I mean, there's all sorts of different things it could mean, but finding the actual area is what we're interested in doing, right? It could represent the work done, total displacement of an object that's been moving. I mean, there's different things we could look at it as representing. But we are trying to just find what this is, right? So the first thing we would do is we go into our tool bag of techniques of integration. We try and come up with the technique of integration to handle that. And so we start going through them, substitution, integration by parts, start trying different things perhaps, and we quickly realize that there's nothing we're going to be able to do. In fact, when I put it into Mathematica, here's what Mathematica gives me as the antiderivative of the general antiderivative of sine of x cubed is -1/2, yes, that's I, the imaginary unit, negative x times the gamma function with the parameters 1/3 and negative ix cubed. What the heck? I mean, so this is like, we haven't even studied gamma functions, all right? You won't see gamma functions for a while. So this really doesn't make a whole lot of sense to us right now, right? Now, if I ask Mathematica to give me the definite integral, which means that I actually put the limits of integration on there, it spits back 0.233845 plus 0I. So imagine this isn't even here. The answer is 0.233845. So the question is, how did Mathematica come up with this numerical approximation? Right? We know that to do it for us, we need to be able to come up with this first, right? And then evaluate this at the two endpoints. We're not going to be able to do that because we can't come up with this. However, because sine is a power series, we can represent in a power series, an infinite series, that's the way we'll attack it. And we're going to be able to come up with the same approximation that Mathematica did. Right? So here's how it's done. What we do is this. Let's start with what sine of x cubed is. Now, we do not need to go through Taylor's formula and all that stuff. We need to just break the book out, and we need to say, what's sine of x? Well, look, this formula here, sine x, look at that now as saying sine of u, all right? And that all you do is you come in this formula and you replace all your u's with what? Whatever we have in our sine. In our sine, we have x cubed, don't we? So what I'm going to do is I'm not going to write this out. I'm going to write it here like this, all right? I'm going to write this right here, replacing all my x's with what? X cubes, right? Because that's what I have, right? This is like sine of x, but for us, x is x cubed. So what is the series? I'm going to start with what? X, so that's going to be x cubed. So I'll have x cubed. And then the next term will be what? Minus 1/3 factorial, right? X to the third, but Rx is x cubed. So this is x cubed, right? Y'all see that? Everything highlighted here is like the x was in the formula. What will my next one be? Plus 1/5 factorial x cubed to the 5th, right? One more. Yes. And it keeps going, right? Now, now what we want to do is we want to integrate this, right? We want to integrate this. So that means we want to integrate both sides. So maybe before I integrate it, let's clean this up. Let's just rewrite this. Let's actually raise these powers out. So this is x cubed minus 1/3 factorial x to the, it's either 6 or 9. 9. Multiply them. If it's power to power, we multiply. plus 1 over 5 factorial x to the 15th minus 1 over 7 factorial x to the 21st plus dot, dot, dot. Now, this is what sine of x cubed is, all right? Now let's integrate. So I'm going to integrate the left side with respect to x, right? Does that make sense? And I'm going to integrate the right side with respect to x. So I'm going to integrate this power series over here. And let's just do each one of these one by one. So this will be equal to, what's the antiderivative of x cubed? 1/4 x to the 4th, right? Okay, now forget the negative 1 over 3 factorial. That's just a constant. What's the antiderivative of x to the 9th? 1/10 x to the 10th, right? So I'm just going to put minus 1 over 3 factorial times 1/10 x to the 10th. Then plus the next one, I'm going to ignore the 1 over 5 factorial. What's that going to be? Antiderivative of x to the 15th. 1/16 x to the 16th. And then minus 1 over 7 factorial times 1/22 x to the 22nd. Isn't that my antiderivative? Yes? Now, I have to keep going forever, right? So now come in here and say, all right, what if you wanted to evaluate this from 0 to 1, right? 0 to 1. Wouldn't that mean that you just want to take this and evaluate it 0 and 1? So let's first plug 1 in. What happens when you plug 1 in? What do you get? 1/4, right? I'm plugging in 1 here. 1 to the 4th is 1. So I get 1/4 minus 1 over 3 factorial times 1/10. Do you see all the x's are going to turn to 1s? So I'm just going to be left with the coefficients, right? 1 over 5 factorial times 16 minus 1 over 7 factorial times 22. Yeah? And it would keep going, so I'm just going to go plus dot, dot, dot. I'm going to close that off. Then I come through and I subtract what I get when I plug in 0. So plug 0 into this, and thank goodness for us, that's nothing, right? 0. Zeroes everything out. And so now I'm going to break out my calculator, which I think I left in my office. Damn it! Please, if someone could, I'd like for someone to try and do 1/4, take away 1 over, let's see, 3 factorial is 6. So this is 1 over 60. Then I'd like for you to add to that 1 over, what's 5 factorial? So, is it 120 times 16? There. So 120 times 16 is what? I don't know. 120 times 16. And then subtract from that whatever you get when you do 7 factorial times 22. And just stop there. Sorry, man, I should have brought my calculator. We're just going to have to trust our calculator people here today. No pressure. I can't believe I forgot my calculator. I believe it, actually. Let me know if you get something. You know? What'd you get? Whoa. Can I borrow it? 1 divided by 4 plus 1 divided by 60 plus 1 divided by 120 times 16 minus 1 divided by 7. I got 0.2338451,479. It's the way you put it in. We can talk about that if you want, but you have to just trust that this is coming out to match up pretty damn close to what Mathematica has. Yeah, and so we are within a certain tolerance. Now, if that tolerance was not good enough, then all I need to go is just keep going out further, right? And at some point, the tolerance is so good that it doesn't matter that you're approximating anymore, right? And if you're building an aircraft, you know, bearing for an aircraft, I mean, you have certain tolerances, but you don't go to like the billionth of an inch. You know, I mean, it's impossible. We can't machine things that precise, right? So there's a point at which you can stop and be okay with this being an approximation. Does that make sense? So, I mean, we didn't need a technique of integration at all. At all, right? Well, we needed to know how to do the antiderivative of a power, which is the first thing you ever learn when you're doing antiderivatives, right? So I hope that convinces you that there is some usefulness to this. And this is the way a computer is going to calculate it. If you could find the power series representation of it, you could do it. But if it was a definite integral, well, I mean, I take that back. You could find some form of an antiderivative, like this was the antiderivative, right? That would be it, a new power series. So you would take your ugly function, you say, what's its antiderivative? Antiderivative, you turn it into a power series, then you integrate it, and you say the antiderivative is this power series. Now, if you want to know the definite integral, then you can plug numbers in. Another classic example of this is this function. This is a function that cannot be integrated in closed form. I have not tried this one in Mathematica. Let's see what it gives me. I say I haven't tried it in a while. So what does Mathematica say when I try and integrate e to the negative x squared with respect to x? Now the error function. So I did show you this. So it can't do it. All right? Can't do it. But for us now that we are equipped with the power series, what we do first is figure out what is e to the negative x squared. Let's rewrite that in a power series. So what I'm going to do is not do Taylor's formula. I'm going to go to the book or go to some table. And this formula now for e to the x, I want you to look at this as really being like e to the u, right? E to the u is going to be 1 plus u over 1 factorial plus u squared over 2 factorial plus u cubed over 2 factorial, right? But u for us is what? Negative x squared. So I'd like for us to please write that down. This will be 1 plus what? Negative x squared over 1 factorial plus negative x squared what? Squared, right, over 2 factorial plus negative x squared what? Cubed over 3 factorial plus negative x squared to the 4th over 4 factorial. Do you see all I'm doing is plugging negative x squared into the formula for e to the x? Replacing x with negative x squared. And I will clean that up a little bit. This will be 1 plus, well, can I write it this way? Minus x squared. What will my next term be? I mean, I put these in parentheses for a reason. You have to pay attention to what's happening here. This was negative x squared squared, right? You square both of these. So like you square the negative, it becomes positive. You square x squared, it becomes x to the 4th. So this is going to become a plus x to the 4th over 2 or 2 factorial, right? Then we'll have, the next one will be plus or minus. Minus x to the 6th over 3 factorial or 6. And we could leave it as 3 factorial. It doesn't matter. The next one would be another one plus, right? X to the 8th over 4 factorial. 24, let's say. And now if someone needed me to integrate that, I could integrate that pretty easily, couldn't I? I could integrate that pretty easily. Term by term integration. So what would the antiderivative of e to the negative x squared be? Well, the antiderivative of 1 would be x, then minus 1/3 x cubed, then plus 1/5 would come out, so 1/10 x to the 5th, and then 7 would come out, 1/42 x to the 7th, and blah, 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 right? Plus some constant of integration, but so this antiderivative here of this is an approximation to this, but I can, again, get it as close as I need it, as I would reasonably ever need it to be. All right. I think that leads us pretty good into what I wanted to show you. This isn't the end of today. Still have a little bit more to do. A very, very nice result. I would like for you to tell me, what is e to the ix? Now, I is the imaginary unit, the imaginary number. Do y'all know the property of I? I is defined to be the square root of -1, right? And I squared is what? Is -1. And I cubed is what? Well, that's I squared times I, right? What was I squared? -1, right? And then times I. So we just write it like this, -I. Do you agree I squared is -1? Then this would become -1 times I, which is -I. You following me? What's I to the 4th? It's I squared times I squared. What's I squared times I squared? -1 times -1, which is 1. Then what's I to the 5th? Yes, or could I do this? I times I to the 4th? What's I to the 4th? 1. So what's 1 times I? It's just I. And then what's I to the 6th? Well, it's going to start repeating itself, right? See, I'm back to I, aren't I? So, aren't I? It's weird. This is cyclical. It's a cyclical thing. It's kind of like when you take -1, right? When you take -1 and you raise it to an odd power, right? You get -1. When you take -1 and you raise it to an even power, you get 1, right? So -1 to a power oscillates back and forth between -1 and 1. So it goes back and forth between two things. When you do I to various powers, it cycles through from I to -1 to -I to 1, then back to I, then -1, then -I, then 1. And then it goes back to I, just kind of like the cosine did with the derivatives, right? So it's cycling through four things. Just point that out first. All right, now let's get back to this. Okay, so what I'm going to do is I'm going to say, well, this is e to something, right? E to something. So forget that it's x, just that's like a u. Replace that x in here with what? Ix. I'd like for you to write this down. Replacing x with Ix. Things are going to get cool. It's 1 plus Ix over 1 factorial plus Ix squared over 2 factorial plus Ix cubed over 3 factorial plus Ix to the 4th over 4 factorial. I'm going to go out a couple more. Ix to the 5th over 5 factorial plus Ix to the 6th over 6 factorial plus Ix to the 7th over 7 factorial. I'm trying to get one more. Ix to the 8th over 8 factorial. You get the idea though, right? According to the power series representation of e to a power, that's what it should be, right? Let's do some stuff to this. All right, this is 1 plus ix over 1 factorial. Now let's square this. Let's actually square this. What happens if you square I? You get -1, don't you? And that's just going to be x squared. So isn't this just minus x squared over 2 factorial? This shit's going to be so cool. Check this out. Okay, what happens if I cube I? I get -I, right? So this is going to be minus I, then x to what power? Cubed over 3 factorial. Okay, next one. If I do I to the 4th, what was I to the 4th? 1. And then x to the 4th. So that's just x to the 4th over 4 factorial. Everybody following me? What's I to the 5th? It's just I. So we're back to I, right? So this is going to be plus I to the, ix to the 5th over 5 factorial. Keep going. What's I to the 6th going to be? It's going to be -1, right? -1. But then x to the 6th, I'm going to go minus x to the 6th over 6 factorial. 2 more to go. What's I to the 7th? So now we're at minus I again. So minus I x to the what? 7th over 7 factorial. Almost there. What is I to the 8th? It's 1 again. So we're at x to the 8th over 8. So freaking awesome, man. I get excited about this even though I've already seen it. Check this out. Does anybody see this? Let me help you a little bit. I'm going to look at all the things that don't have I's in them. Anybody recognize that series right there? What is that? That's cosine. Isn't that? That's cosine x. Everyone agree that that's cosine x? So I'm going to say that's cosine x. And then, what is this series right here if I were to take an I out of each one? Isn't it sine? So factor an I out of everything I haven't touched with yellow. Factor an I out. So you mean factor an I out and then put sine x next to it? And I'm supposed to add these two together? Right, because it's a sum. Has anyone ever seen this before? That e to the ix is equal to cosine x plus I sine x. Anyone ever seen that before? It's called Euler's formula. All right. Now, for those of you who've seen some imaginary number stuff, do you remember seeing that all imaginary numbers can be written a plus bi? All right? Where a is called the real part and b is called the imaginary part, if you've seen complex numbers. What this kind of is alluding to is that every imaginary number, right, because this is like a plus bi, it's just kind of telling us that every imaginary number can be rewritten this way. In fact, let's try some things like, what if x is 0? If x is 0, what does this Euler's formula tell us? E to the I times 0 must be what? Cosine 0 plus I times sine of 0. All right, well, what's e to the, well, I times 0 should be 0. What's e to the 0? 1. And then over here, what's cosine of 0? 1. And then what's sine of 0? 0. So that checks, right? I mean, that appears to work. What if x is equal to pi over 2? You get e to the I times pi over 2 is equal to cosine of pi over 2 plus I times sine of pi over 2. So what does that give you? E to the I times pi over 2 is equal to what? What's cosine of 0? I mean, sorry, what's cosine of pi over 2? No. 0. What's sine of pi over 2? 1. So that's just I times 1, which is I, isn't it? So what I'm really saying here is that e to the I times pi over 2 is equal to I. I know I'm starting to lose some of you, and that's okay. All right? That's what the last few days of class is all about. All right? This is a huge deal, all right? Because what it does is it gives us a way of representing a complex number in a way we hadn't looked at before. All right? What we're saying is I is this. This is what I is. Now, I'll decide here in the next few seconds if I'm going to blow the doors completely off or not right now. But let's get to the formula I told you is argued to be the most beautiful formula in math. It is the formula e to the I pi plus 1 equals 0. It's argued to be the most beautiful formula in math. I don't necessarily agree with that, but you hear people talk about it all the time. If you Google it, that'll probably pop up. All right? Now, here's why it's argued to be the most beautiful formula in math. Because it contains everything that's important in mathematics. First of all, I'll start with the one that's more obvious, the number 1, right? How important is the number 1? How many times do we multiply something by 1 and we do something tricky, something over itself, right? And then we just, to simplify things, or back in Cal 1 when you're trying to do like, doing limits and you multiply top and bottom by something, we're always coming in with the 1, right? And in our mathematical system, the real numbers, 1 is called the multiplicative identity. One times anything, right, should be that anything. It's the identity. It's the only number that when you multiply by that, it leaves that stuff alone, right? Doesn't change it. The next important number in here is 0. 0 seems like maybe I should have started with that, but 0 actually, when humans were coming up with the number system, if you believe that, that 0 actually came after we came up with the number 1, 2, 3, 4. 0 was like a huge thought. The idea of nothing was like big time. So 0 is actually what we call the additive identity. Additive identity, right? If you take anything and you add nothing to it, you stay the same. So we call it the additive identity. Have any of you ever heard of the field axioms? The 12 field axioms. Our number system is based on these 12 properties. For you math people, math majors, you'll be bathing in this shit later, okay? I mean, it's what do? You start with the number system and you try and show that all these different things exist in that system. If they don't exist, if you don't have all 12, it's not called a field anymore. Maybe it's called something else. It's not as strong as a field, okay? So you also need to have 2 operations on a field. We have 2 operations on our number system. Multiplication and addition, right? That's it. Division is multiplication. Subtraction is addition. So we have 2. So you have 2 what we call binary operations. We have these different structures. One of the structures is that it contains a multiplicative identity. It contains an additive identity that takes care of both of the operations in math, right? Again, I'm going beyond what I need to be going into here. That's why 1 and 0 are important. Now, e. Well, we all know e is that base of the exponential function that is the only function that exists, which is its own derivative, right? That was the only one. It's unique. And so we called it the natural exponential function because we can't quite explain why it is that e is the only number that does that, but it is, and so it's our very important number, right? Pi is the ratio of a circle's circumference to its diameter. right? Any circle you draw, you take the circumference, you divide it by the diameter, you'll always get pi. And then I is the imaginary unit, which for a long time mathematicians were like, nah, imaginary numbers don't really have any value. And then we discovered later that they do, and they're just as real numbers, and that's a whole other argument we won't even get into. But all these numbers are extremely important in mathematics, and this is one simple equation that connects all of them together. And I claim that right now you can actually show me it's true. Because what is e to the I pi according to this? E to the I pi is just cosine pi plus I sine pi. What's cosine pi? -1. What's sine pi? 0. So this is just -1, right? What's -1 plus 1? 0. Right? But you have to believe in Euler's formula, but you have to believe it now because I created it from this. But I don't know if you have to believe it. But that was pretty nice how we pulled cosine and sine out of here, right? I remember this is a problem that you want to stump someone. You can usually stump someone pretty good with this one, even if they've seen a lot of math. What's I raised to the I? That doesn't seem like it would make a whole lot of sense, would it? What's I raised to the imaginary number I? Okay, so it's the square root of -1 to the square root of -1, but what's that? I don't know. Okay, so look, check this out. Do you remember when I just said right now, right here, that this was another way to represent I? Okay, I want you to replace the I in the base with this right here. E to the I pi over 2. All right, so I'm going to come here, I'm going to say this is equal to, the base I'm replacing with E to the I times pi over 2. And what am I raising this to? The I. What happens when you take something to a power? What do you do to these powers? Multiply them. What's the I times the I going to become? -1, right? And then I have the pi over 2 still. So this is just e to the -pi over 2, which is a number. That's a real number. It's a real number, right? I mean, you could type into your calculator e to the -pi over 2. Most people who have not studied complex numbers would not know this. So if you ever want to kind of mess with someone, that's a good one. Okay, I'm losing track very quickly here. But what we're going to do now is we're going to take a look at two operations that we have for power series. We need to be able to multiply and divide power series. Right? We need to be able to come up with some way of doing it. And I have two examples to show you. And then hopefully if I have time, I will be able to show you one other cool thing. So first one, we're going to multiply we're multiplying power series. All right. Find the first 3 terms of the Maclaurin series for f of x equals e to the x sine x. Now, the problem that we have here is that we have multiplication, right? We have multiplication between these two things. So I would like to figure out what's the Maclaurin series for this. Well, you could go through and try and figure out the Maclaurin series, couldn't you? Like take derivatives and all that crap. Or you could go to this table, but the table has e to the x by itself and sine x by itself. And so what we're supposed to be doing is taking the e to the x and the sine x and multiplying. So that means let's take the series and multiply them together. Use the fact that we have the table, right, to figure out what e to the x and sine x is, and then multiply those two together. And the question just becomes, how do we do it? So do you agree that this is the same as, what is the power series for e to the x? Give it to me term by term. Don't give me the sigma notation. 1 plus x squared over 2 factorial, x cubed over 3 factorial. I'll just go one more. X to the 4 over 4 factorial plus dot, 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 right? Okay. I'm supposed to multiply that by the power series for sine. What's the power series for sine? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus dot, 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 dot. So we talked about this a long time ago. I said, how would you multiply these two things out? I mean, you can't, right? It goes forever. But what we're going to do is, like you would think. We're going to take this 1, distribute it, and then take the x and distribute it, right? Are y'all kind of okay with that? I mean, it's going to take a while, but that's what we would do. So what we like to do instead is, I don't know if you remember this, but if I want to take 234 and multiply that times 42, do you remember what we did here? We go here, and then here, and then here, and then you go here, and here, and here, something like that. That's the way some books do it, where they will line one up under the other and then do that. I just like to distribute. I just like to go here to here. What's that? X. So I'm going to just write X down. Okay, what's here to here? Negative X to the 3rd, right? So it's the same thing. And I'll have a bunch of those. All right, same exact thing. And then I move on to the next one. When I do the next one, right, this times this, I'm going to get what? X squared. So then x to the 4th, right? So what I'm going to have is, I'm going to want to add to that those other terms, but none of them add to these. These are all odds, right? So I'll put this, you can put it underneath if you want. I'm trying to figure out what would be the best thing to show you here. Let me put it over here. I have x squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial minus x to the 8th over 8 factorial, 7 factorial. So all it did was just brought all these powers up, right? Okay, now I'm going to do another one, here to here. So what's the first one I get there? X cubed over 2 factorial. Wouldn't that line up with this one? That's an x cubed term. The 2 factorial is a number, right? So I'm going to put that under here. Is it plus or minus? It's plus, right? I'm doing that. So it'll be plus x cubed over 2 factorial. What I just did was this one times that one, right? Now do the x squared over 2 factorial times x cubed over 3 factorial. That's what? X to the, so negative x to the 5th over, you put 2 factorial times 3 factorial. Okay? And what would the next one be? Positive x to the, I think we're at 7 over 2 factorial, 5 factorial. Now remember, we're going to be adding this together with this, with these. And what I'm doing is I'm lining them up so that when I add them, they're kind of grouped together in columns. Do y'all see that? And now I move to the next one. The next one would be here, which would be, let's see, here to here, x to the 4th over 3 factorial. So that'll be over here, x to the 4th over, 3 factorial, 3 factorial. So that's this right here times this. Now x to the 6th, negative. X to the 6th, and what is it? 3 factorial times 3 factorial. Let's go another one here. This times this one, x to the 8th. So plus x to the 8th over 3 factorial times 5 factorial. And I think that's good because what was it asking for? What were we asking for? The first 3 terms. That means starting from the lowest power of x up. What is the lowest power of x we have here? Just x, right? That'll be my first term. Do we have any x squareds? Yes. Do we have any x cubes? Here. Well, here. You with me? And notice that if I kept going here, right? If I kept going, all of these are going to be like x to the 5th and then x to the 7th. So those are like bigger than anything else I have. So what are the first 3 terms? X minus plus x squared, and then minus, watch the way I do this, x cubed over 3 factorial plus x cubed over 2 factorial, right? Then plus a bunch of crap out here I don't even care about. This is x plus x squared. Then what I'll do is this, plus x cubed I'm going to factor out. What's left inside here? And one of them is negative, right? So I could go negative 1 over 3 factorial plus 1 over 2 factorial. Plus dot, 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 I don't even care. These are the first 3 terms. It's tedious, right? It's a little tedious. But you kind of hopefully get the idea. Questions? Yeah, it's not a simple thing. I mean, it would be nice if you could just take the 2 formulas, like the formulas for them and multiply. You can't. It doesn't work. Yes. I'll probably give you the first 20 terms. No. No, it would be like first 3 terms. I'm going to give you another one. We're not going to work through it, but just as something to look at. First 3 terms. Actually, I want to show you this. Let me go to YouTube real quick. See if did I show you this? Worst teacher ever? I did, right? All right. So I want to bring it back up one more time. This guy, yeah, I know, right? Wow, there's an advertisement for this video? It's got a lot of views. See, I have to keep moving my mouse. I know. Hold on. Where is he? This has got to be a different video. I don't think this is the same video. That's weird. Yeah, they refilmed it for him. I don't know. No, that's got to be it. No, this is a different video. I've seen this one, I believe. It's a different one. Maybe the other one's gone. I don't know. Anyway, if you go back and watch my video, when I showed this video early in the semester, there was a part where he said, "Oh, you just divide 1," and what it was a power series being divided into 1. So it was like 1 divided by a power series. That's what it was. And the next line just showed what that was. And the students couldn't understand how 1 divided by that power series came out to be the next line. And so he thought they were just jacking with them, all right? Because he appeared to think that was something trivial. So if we look at the first 3 terms of something like cosecant x. Well, cosecant x is 1 over sine x, isn't it? which we could say is the same as 1 over, and then what's the series for sine? X minus x cubed over 3 factorial plus x fifth over 5 factorial. One more, x to the 7th over 7 factorial plus dot, dot, dot. Okay? Yes? Now that I think about it, I've got 8 minutes. On my playlist, I have my reply to him. Or not my reply. There's a horrible teacher. This will at least bring up the problem that you can see what it was. Why is that so slow? Oh, okay. Man, it's hard to see this. That damn parabola thing up there. Y'all see the 1 up here? And then it was 1 over, this is exactly what was on his board. 1 over x cubed, in parentheses, a power series right here, dot, dot, dot. So what he did and didn't show was he pulled the 1x over x cubed out here, right? And let me see. Oh, this is what it turned into. This turns into this, right? How does that happen? Well, you take the 1 over x cubed, forget about that, right? Forget about the x cubed here. Do 1 divided by this, right? That's 1 divided by power series. How do you do that? Well, here's how you do 1 divided by a power series. You go old school division. If you remember your old school division, right? And you put 1 in here, right? And then you say to yourself, all right, I'm trying to come in here, multiply x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, dot, 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 right? Into that. How do you think we're going to do that? Like what? Yeah, how are you going to turn x into 1? Multiply it by what? 1 over x. So look over here. On this one there was a 1, so I didn't have to do it, right? But on this one, let's try it. Let's do 1 over x. What would you get? If you multiply by 1 over x, you have to multiply everything by 1 over x, right? So do 1 over x here, and what do you get? 1 here. And then what's 1 over x times this? Minus x squared over 3 factorial. And then the next one would be plus x to the 4th over 5 factorial. And the next one would be minus x to the 6th over 7 factorial, right? You all understand that? And now I come through, and just like we did with old division, we subtract this row, right? Which changes all the signs. And then we add straight down. So what are we going to have left when we add down? Nothing, and then x squared over 3 factorial, right? Minus x to the 4th over 5 factorial, then plus x to the 6th over 7 factorial. Now you go and repeat the process. How do I turn x into x squared over 3 factorial? I multiply it by what? X over 3 factorial. So I multiply by x over 3 factorial. You see that? And then I go through the process again. And then I go through it again, and again, and again, until I get enough terms of the series to be satisfied. Make sense? Yeah, well, yeah, so on this one, I have it somewhere in here. I'm not going to be able to find it. Yeah, you ignore the 1 over x cubed, because in what he did in class, what it turned into, the 1 over x cubed is still here. You see? So he was trying to show this step to this step. The students didn't understand how 1 over this turned into this. And so after you get here, you just distribute this through. But it's funny, if you listen to the video, there's like, this guy's like adamant. There's no mathematical way that can happen. That one divided by that, all that can turn out. It's like, okay. Well, you'll never get a remainder because it's an infinite series. So you could never stop this, right? Yeah, that's why we were asking, show a certain number of terms. 3 terms is good enough for you being able to demonstrate to me you know what you're doing. But in a class like this one, I think was like a differential equations, you probably need more than just 2 or 3. Where? Right here? That's what happened. That's what happened with the division. I think that's what kind of troubled everyone, is that they were like, well, wait a minute, this looks very similar to this, right? Like 1 over this looks very similar. It's like x squared over 4, but this one was negative, this one's positive, and this one has 7, 192, this was 5, 192, and it's like factoring an x squared out of something. If it's contained in all the terms, you just that's my daughter's drawing, by the way. If I have like 1 over x cubed minus x squared, I can rewrite that as 1 over x squared times x minus 1, right? And I just ignore this for now, right? This is like a 1 over x squared. What's this? I could rewrite that, as using a series, right? I mean, so the x squared stays out there, 1 over x squared. Okay, I've exhausted the time. I believe I've covered everything I want. Homework, I'll send you an email for the homework for this section. I haven't given you anything out of this yet, right? 8-7? Next class will come and we'll talk parametric equations. I would encourage you, if you have a graphing calculator, to bring it. How many of you have a graphing calculator? Anyone not have one? Don't have one? Okay. Have you ever used one? Okay. Are you familiar with like a TI? Okay, I'll bring my TI and you can borrow mine. What I want to show you is how you can use your calculator to graph parametric equations. So everyone bring their stuff. Have a good day.